Well, hi team, chemistry coach coming at you. Coach! We have spent a lot of time looking at these Lewis structure rules or tips or steps or however you want to call it. And again, might be a little bit different than what a lot of textbooks say. And they both work great, but I just prefer that step 2 where you calculate the 6n plus 2 minus number of valence electrons. Allows you to predict ahead of time whether you got multiple bonds, an expanded octet, electron deficient species, carbon rings. I love that predictive power. I don't feel like I'm just throwing dirt at the wall or mud. What is it? Throw mud at the wall and see if it sticks, which the traditional method is. You're like, okay, this goes here. But you know, they all work, which is great. But here, I want this step 2 to match your prediction in your Lewis structure. Like I said, I'll give you partial credit for that. So if you predict 2 multiple bonds and you have 2 multiple bonds in your Lewis structure, even if it's wrong, there's a connection there. I can give you some partial credit. But if you predict 2 multiple bonds and you only have 1 in your Lewis structure, something's off. If you predict an expanded octet and you don't give me an expanded octet, that you're showing you don't have see the connection there. That's what I'm looking for. All right. So again, when you do the 6n plus 2 minus number of valence electrons, again, 6n plus 2 is the number of electrons needed for all single bonds. Number of valence electrons from step 1 is how many you have, right? So again, if that value is 0, you have all single bonds, no funky business. But if it's a positive value, that means one of 3 things. Either you've got multiple bonds, and every value of plus 2 counts as a multiple bond, an extra line in your species, right? Or you have an electron deficient species, which we'll do in a separate video. That would probably be boron, beryllium, or aluminum, or an odd electron species called a free radical. We'll see that. Or it could be a carbon ring. Well, pretty easy to eliminate carbon rings. You need at least probably 5 carbon atoms, 5 or 6 carbon atoms. So if you have less than 5 carbon atoms, let's just eliminate that option. If you don't have boron, beryllium, or aluminum, or if your number of valence electrons is not odd, it's not going to be electron deficient. So most commonly, it's going to be a multiple bond. Well, definitely in this particular video, because that's all we're focusing on. We'll do the other ones later. We'll do all those other ones. So here's the way to think about it. You calculate this value from step 2. If you get a value of plus 2, that would mean you have 1 multiple bond, which means it has to be a double bond, because the single bond is the main, it's the foundation. 1 extra line is a multiple bond, 1 beyond the single bond. That's what the multiple bond means. So if you have a value of plus 2, it has to be a double bond, assuming it's not an electron deficient species or a carbon ring, right? If you get a value of plus 2, and they're multiples of 2, that would mean you have 2 multiple bonds, because every positive 2, that's 2 electrons in the extra multiple bond, right? Well, 2 multiple bonds could be 2 separate double bonds in different areas or locations of your Lewis structure. So it should be some complex molecule, probably some organic molecule, or it could be a triple bond, because a triple bond is the single bond plus 2 extra lines, 2 multiple bonds, right? You don't know which ones that's going to be until you draw the structure and try to give all the atoms their preferred number of covalent bonds. So that's pretty easy once you do that skeleton. If you have a value of plus 6, that's 3 multiple bonds. So that could be 3 double bonds, right? Somewhere in the species. Or you could have a triple bond somewhere and a double bond somewhere else. That counts. And then you could go to plus 8, plus 12, and then you're getting really complicated stuff. You won't see too many more than plus 6 or plus 8 in this class. So that's your thinking process, but I'll show you when you get a positive value, eliminate organic rings, eliminate electron deficient species, boop, and then it's got to be this. All right, so I always try to eliminate those first. So let's look at some examples, yay! All right, let's do a couple examples. We'll start easy and get harder and harder. So I want to start with simple molecules, and then we'll get into ones where we have multiple central atoms. So let's do the Lewis structure for diatomic nitrogen. The phase is irrelevant when you do the Lewis structure. It doesn't matter if it's solid, liquid, or gas. That's irrelevant. But you happen to know nitrogen's about 78% of what you breathe, assuming you're breathing normal air, right? Okay, not on some other planet or something. So nitrogen obviously doesn't even have a central atom. It's just 2 of them. Boop, and that's it, right? So we technically don't have a central atom. So let's go through and do that. Actually, ideally, look at those steps. Step 1, calculate number of valence electrons. Step 2, do the 6n plus 2 minus the valence electrons. Step 3, central atom. Step 4, skeleton. Go through and do all those steps. See if you get the same thing I do. Should be pretty simple. So I will go ahead and do this. So let's do number of valence electrons. And I'm not going to write the steps in there. A lot of times I merge a few steps. Well, we've got 2 nitrogens, right? So we've got 2 nitrogens. let's see what group they're in. Where's my periodic table? That's one of the pnictogens. So 1, 2, 3, 4, 5A. So nitrogen has 5 valence electrons. So 2 times 5 equals 10. All right, so we got 10 valence electrons in the pot to sprinkle through the nitrogen atoms to satisfy their octet rules, and ideally their preferred number of covalent bonds. So how many covalent bonds does nitrogen prefer? Well, it's 1, 2, 3 away from neon. So nitrogen prefers 3 bonds. That could be 3 single bonds, or a double bond and a triple bond, a double bond in a single. Wait, so no, yeah, that'd be a triple bond, or 3 single bonds, right? Or a double bond and a single bond. Apparently, I can't count to 3. I'm like, right? So a lot of options with 3 bonds. Let's do the 6n plus 2 minus the number of valence electrons. So this would be step 2, right? So what's n? N's the number of non-hydrogen atoms. So n will be 2 in this case. Right on, because there's no hydrogens in nitrogen. So that will be 6 times 2 plus 2 minus 10. Let's see what we got. So 6 times 2 is 12. That's usually where I screw up. 6 times 2 is like 914. So 6 times 2 is 12 plus 2 is 14 minus 10. And you can do a lot of that in your head. You don't have to show every step. I just do that because I want you to, if you don't know where I got my number, I need you to be able to track it. But when I'm doing this, I just do that all in my head, right? But ideally, just do this. So I can see what 6n plus 2 is, and I can see what the number of valence electrons is. At least I can see what you're thinking. Again, this is a neutral species. You don't have to worry about it. So 14 minus 10 is plus 4. What does that mean? Well, we can, obviously there's no carbon rings in there. There's no carbon, right? So it can't be that. We'll see for electron deficient species, we're looking for boron, beryllium, aluminum, which is not one of those. We have an even number. If it's an odd number, we'll find out that might be an electron deficient species. So it's got to be multiple bonds, and it's 2 factors of 2. So that means we have 2 multiple bonds. Ooh. Now that could be 2 double bonds or 1 triple bond. It should be intuitively obvious when you do your skeleton after that. So obviously we have no central atoms. We just have 2 nitrogens connected to each other. That's pretty easy. So let's draw the skeleton. We got a nitrogen and a nitrogen. Obviously we have to have at least a single bond here. Now if you want to do the dots, you're welcome to, or you can do the lines. So we'll do dots first, right? So there's the single bond, but we have 2 multiple bonds, which means we need 2 extra here. I'll do them side by side. So that pair of electrons represents that one line, that single bond. I need 2 multiple bonds. They have to go in between, so which means I must have 2 extra pairs. That's why it's the plus 2, or 2 extra lines. You see the single bond plus the 2 extra lines, that's the 2 multiple bonds. So we have no option but to do that, right? There's no other place it could go. So this predicts a triple bond between the nitrogen atoms. Well, now let's complete our octets, right? So we've got, they both get to share those 6 electrons. 6 is not 8, which means each nitrogen needs 2 more electrons. So we're going to do that as lone pairs. And it doesn't matter if you put the lone pair here, here, here. It will when we do shapes later with Vesper theory, but for the Lewis structure, it doesn't matter. You can put the lone pair up there, you know, it's irrelevant. So now let's count the total number of bonds they have. So nitrogen prefers 3 bonds, 1, 2, 3, 1, 2, 3, so they're happy. We have 2, 4, 6, 8 electrons, octet rule satisfied, 2, 4, 6, 8 octet satisfied. So we've satisfied the octet rules for both nitrogen atoms. We've satisfied we have to do that. We've satisfied the preferred number of covalent bonds. That's not a rule, you know, made in stone, but it's a good guideline. So that looks pretty good, actually. Let's count the number of, let's check it, that last step. How many electrons did we use? 2, 4, 6, 8, 10, or 2, 4, 6, 8, 10. 10 equals 10, yay! So we know that that's correct, and that's how you deal with species with multiple bonds, every positive 2. Let's do one for a complex molecule with multiple central atoms. Ho, ho, ho. All right, let's do this one, and this one looks similar to the ethanol one we did. Remember we did CH3, CH2OH. This one's flipped, though. The H is not on the outside of the O, which means that hydrogen's connected to the carbon, not the oxygen. Ho, 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 Merry Christmas. So go ahead and pause this, right? Do step 1, number of valence electrons. Step 2, do the 6n plus 2 minus valence electrons. See if you can predict what's in there. Draw the, figure out what your central atoms are in step 3. Draw the skeleton in step 4. Fill in the octets. Step 5, move your way through. Give it a shot while I get this cat hair out of my eye. I'll be right back. All right, did you get what I got? So step 1, let's calculate the valence electrons. You don't have to show this work ever for my class. You can just go 4, 5, 6, 7, 11, 12, right? 18. You can just count it up if you want to. But if you're having trouble at this point, just look at the number. We have 3 elements: carbon, hydrogen, oxygen. How many carbons do we have? We've got 2 carbons. How many valence electrons? Group 1A, 2A, 3A, 4A. So carbon has 4 valence electrons to throw in the pot. So 2 carbon atoms times 4 valence electrons each is 8. So the 2 carbons do a total of 8. We've got 1, 2, 3, 4 hydrogens. Obviously, hydrogen's only got 1 valence electron. So 4 hydrogens times 1 each, a total of 4. So we got 8 plus 4 is 12. We've got 1 oxygen. Oxygens, the chalcogens, 1, 2, 3, 4, 5, 6 valence electrons. So add 6 to the 12, you get 18 valence electrons, which is an even number. If it's an odd number, that's going to fall into one of the electron deficient species categories called a free radical. All right, let's do our step 2, 6n plus 2, where n is 3, carbon, carbon, oxygen. You don't include the hydrogens, right? So n is 3, so 6 times 3 is 18 plus 2 is 20. So that's the number of electrons we need for all single bonds, but we only have 18, so 20 minus 18 is plus 2. We don't have enough electrons to get all single bonds. There's 2 carbons. That's not enough to make a ring, right? We need 5, at least 5, usually 6. So no carbon rings, no electron deficient species, no boron, beryllium, aluminum. This is an even number. So it's got to be a multiple bond. Plus 2, multiple bond. 1 multiple bond has to be a double bond. I know before I draw this skeleton, there's going to be 1 multiple bond in there. Well, let's do it, right? Now, hydrogen has to be terminal. It can't be central. Oxygen's pretty electronegative, right? It's farther over than carbon. More electronegative over here. So carbon's less electronegative. So carbon loves to be in the middle, loves to be a central atom. And there's 2 of them, so odds are the carbons are connected together. And when you look at this, these 3 hydrogens are written there because they're bound to that carbon. This hydrogen is bound to that carbon, right? So let's think about it. Now, where's that oxygen go? Let's take a look at it. Let's draw the skeleton. So here's my first carbon. I'm not going to do the dots anymore. I'll just do lines. So here's my first carbon with 3 hydrogens. I like to do those on the left, the right, and the top. Remember, you got left, right, top, bottom, because I like to work and meander my way over to the right, from left to right. So think of that as carbon number 1. Now that's got to be connected to carbon number 2, right? Which has a hydrogen on it. I could put the hydrogen here, here, here. Doesn't matter. It's completely irrelevant, right? Now, the question is that oxygen connected to the hydrogen or the carbon? Could I put now watch this. Could I put the oxygen there? No, because that gives that hydrogen 2 bonds or 4 electrons. So that disobeys the octet rule. Hydrogen cannot be a central atom. The only place that oxygen can go is on that carbon. It's the only place. Right? And it makes it terminal. It's highly electronegative. They like to be on the outside or terminal. So everybody's kind of happy here. Less electronegative elements in the middle. That's step 3. Now, let's do step 4. Here's the basic skeleton. Where's that double bond go? All right. Carbon prefers how many bonds? Well, 1, 2, 3, 4. So carbon will always have 4 single bonds or 2 double bonds or a triple bond, single bond. So 1, 2, 3, 4. That already has 4 bonds or 8 electrons. It's done. This carbon has 1, 2, 3 bonds. Oh no, it's not happy. It would like 1 more bond. There's no more atoms to stick there. Oxygen prefers how many bonds? 1, 2. It only has 1. Wouldn't it be a beatific thing if we stuck a double bond there? Oh, yes, right? See that double bond? Now it gives oxygen 2 bonds. That's what it prefers, and it gives carbon 1, 2, 3, 4 bonds. Everybody has their preferred number of bonds. Isn't life good? And that's it. Now let's do the next step. Let's add the lone pairs to complete the octets. 2, 4, 6, 8. 2, 4, 6, 8. Carbon rarely has lone pairs. Duet rule for the hydrogens. Let's check the oxygen. 2, 4. That's not 8. It needs 4 more electrons. So we're going to put 2 lone pairs on there for get 2, 4, 6, 8. Now the octet rule satisfied. So everything has 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Octet rule satisfied for both carbons and the oxygen. Duet rule for all the hydrogens. Everything is rocking and rolling there. Let's check it. Okay. Again, all the preferred number of covalent bonds are good. All the octet rules and duet rules satisfied. Let's count the total number of electrons, and it better equal 18. If it isn't, we either screwed that up or screwed this up. You ready? 2, 4, 6, 8. Who do we appreciate? 2, 4. Sorry about that. I was in the marching band and did all the football games. 2, 4, 6, 8, 10, 12, 14, 16, 18. 18 equals 18. Boom! Thank you for full credit on the exam, Professor Locks. You want to do a harder one? Yes, let's do one more that's really difficult. Before we do a harder one, I wanted to point this out. See how we have 2 central atoms here? Everybody see that? So these are both central atoms. I'll put these in blue because they're bonded to more than one other atom. So we have 2 central atoms, carbon 1 and carbon 2. That is no longer a simple molecule. A simple molecule has 1 central atom, so this makes this a complex molecule. Right? So anything that has more than more than one, so 2 or more central atoms, we're going to call that a complex molecule. That's going to give us some issues when we do shapes later, because we're going to find out we can do the shapes about each central atom, but not the entire complex molecule. If it's a simple molecule that only has 1 central atom, then the shape of that atom is the shape of the molecule. Makes life a little more simple. Let's do a tough one. You ready for a doozer? So here's a complex organic molecule. You're going to do this all the time. This is one of the most important things you can learn in this class if you're moving on to organic chemistry, biochemistry, biology, and looking at structures of, carboxylic acids and alcohols and amines and all that fun stuff. If you get the Lewis structure wrong, everything goes, right? You get the shapes wrong, reactivity wrong. But you're going to get weird stuff like this, and they love the condensed structures, right? The condensed structural formulas. So we've got, let's do the Lewis structure for CH2Br, CCCOOH. A lot of times you'll see that as CO sub 2H, CO2H, or the Cu group. Turns out that's a carboxylic acid. If you want to go back and review, I think in one of the earlier topics on compounds and stuff, we did structures, different types of structures. And then I talked about functional groups, right? All the different kinds of functional groups of organic species, carboxylic acids being one of them. They have a very specific structure on one of their 2 ends, or possibly both ends. Do this for me. See if you can pause this, go through and work this on your own. The more you do it, the more you'll see patterns. Oh, carbon, there are 4 bonds, right? Halogens like to be on the outside, yada, yada. You'll start to see patterns. You'll get used to the 6n plus 2 minus the valence electrons. And even if it's kind of weird at first, I think you'll start to appreciate it. Be like, I love this one. It was kind of weird because I always did it the traditional way that most textbooks teach it. But when I learned this way, once I got over the, kind of how different it was, anything different is kind of, it's like brushing your teeth with one hand and then switching to the other hand. It's weird, but after 3 weeks, after 21 days, it becomes normal. It's hard to go back. Kind of like now, we're teaching remote now. If we do it long enough, we're going to get used to it, and it'd be really weird to go back. Even though I always prefer to be face-to-face with you guys. I love to yuck it up in the labs and get to know you guys real well. So I miss you so much. All right, here we go. So did I talk enough? Are you done already? So on tests, you should fly through these. Because you can do this in your head. You can do most of this in your head as you're moving along. I'm a little more careful because I tend to miss the simple things, you know what I mean? I get the harder stuff right. But if I'm doing, 3 times 4 plus 2 times 6, I'll get that wrong. It's like I have a hard time balancing my checkbook with just my head. I can do complex math. I screw up my checkbook at the end of every year. I'm off by $312.18. How did that happen? Right? And it's always against me. It's always less than I thought. It should be equal. Either half the time I have more money in the bank account than I thought, and half the time less. It doesn't seem to work out that way. Like a conspiracy theory. All right, here we go. Hopefully I've talked enough. let's calculate this. So we've got a lot of atoms in here. Lots and lots and lots. So we could just do this in our head if we want to, but let's count it out. We've got 1, 2, 3, 4 carbons, right? And carbon again is in group 4A. 1, 2, 3, 4. 1, 2, 3, crunch. We've got hydrogens. 1, 2, 3. Is that all we got? 3 hydrogens? I'm running out of space. 3 hydrogens, 1. Let me write this up above here. Where did my purple pen go? I'm going to write this up here. CH2 BrCCCOOH. That's just insane looking, right? It's just a big, scary looking dog barking, and then you go up and goes, right? That's all this is. It barks really loud, but when you do it, you're like, oh, that was a really nice one. You'll see patterns. We got a bromine here, but I only got 1 bromine, so we haven't stuck that in yet. Well, how many electrons does bromine fall? The halogens. 1, 2, 3, 4, 5, 6, 7A. So all the halogens sprinkle 7 electrons into the pot. We got 2 oxygens. Do you see that? All the chalcogens are in group 6. 1, 2, 3, 4, 5, 6, right? All the chalcogens are group 6. This is where I screwed up. Right? So 4 times 4 is 16, 19, 26, 36, 37. Is that 38? Oh, please tell me it's 38. Let me double check it again. It'll be 12, 19, 22, 32, 30. I think it's 38. You know, call me if I got it wrong. That's usually where I screw up. The stupid number of valence electrons, right? 16 plus 3 plus 7 plus 12 is 841. All right, I find this easier. So what's N? Get rid of the hydrogens. So we got 1, 2, 3, 4, 5, 6, 7. All right, we got N is 7. 1, 2, 3, 4, 5, 6, 7. Okay. Well, let's calculate 6n plus 2. Is this a little scarier than the other ones we did? It's the same thing. So we've got 6 times 7, 42, 3, is that 44? So let's go 6 times 7 plus 2 minus 38. So 6 times 7, 42, 43, 44 minus 38. Ooh. So we need 44 electrons for all single bonds, but we only have 38, so we're 6 short. What you want, Paige? Hey, kitty. His seat's gone. Now, 1, 2, 3 carbons, not enough for a ring, so we don't have a ring structure. No boron, beryllium, aluminum. This is not an odd number, so it's not an electron deficient species. So this is multiple bonds. That's 3 multiple bonds. Hi, Paige. What do you want, buddy? So that could be 3 double bonds, or a triple bond, and a single bond. Well, let's see. All right, let's do the structure here. Bromine's it's a halogen. They like to be on the outside terminal. Hydrogen has to be terminal. Remember oxygens? I'll show you the oxygens are going to be a trouble there because it looks like from the structure there, the formula, that they're connected together. But would you agree that these 2 hydrogens for sure are on that carbon? So I'm going to show you some wrong ways first. So let's take that first carbon. Let's connect the 2 hydrogens, all right? Now, is it connected to the bromine? Then to the carbon? Is that going to make bromine very happy? You know, a halogen like that? Halogens prefer 1 bond, right? So if you look at all the halogens here, they're only 1 away. So they don't want 2 bonds, they only want 1. So that's highly unlikely, and it leaves the carbon unsatisfied. So what this probably means is that bromine is also connected to that carbon. You see that? So let's stick the bromine down here. Not going to put the bromine here or here, doesn't matter. And that carbon's connected to that carbon. Carbons love to connect together. Welcome to organic chemistry. You'll take a whole year of that probably. So there's carbon number 1 with the 2 hydrogens and the bromine stuck on it, connected to carbon number 2. Doesn't look like there's anything other than another carbon connected to it. So carbon 1, 2, 3, and then another carbon connected to that. We got a big old chain here, right? Like a bunch of like trains connected on a train track. So carbon 1, carbon 2, carbon 3, carbon 4, 1, 2, 3, 4. Now there's obviously, do you see this hydrogen right here? That hydrogen is connected to one of those oxygens. It's not connected to this carbon. But the oxygen is definitely connected to that carbon right here. The problem is this oxygen right there. That second oxygen. What do we do with that? Would we do this? That's kind of what it looks like, right? But remember the rules. You want to avoid highly electronegative atoms connected together unless you're forced to, like O2 or O3, like diatomic oxygen or ozone or something like that. Or if it's a peroxide, I would tell you it's a peroxide. This is not a peroxide. So this is highly unlikely. Possible, but highly unlikely. So now if you try it with that, you'll find out this won't work. No matter what you do, this will not work out. So what happens is this oxygen is also connected to that carbon. All right? So let's erase this. It's not always stress. Sometimes you'll do the wrong Lewis structure and you go, something's off here. So you got to go, well, maybe my atoms aren't connected right. That's why this is called a skeleton. So the 2 oxygens are connected to the carbon, and then that hydrogen is connected to one of the 2 oxygens. That's a pretty ugly oxygen right there. So this would be the basic atom connectivity that would make the most sense. Bromine doesn't want to be in the middle. Hydrogen can't be. The 2 oxygens don't want to be connected together. And this is the COOH carboxylic acid group you might be familiar with. We've got 3 multiple bonds to stick in here. Ooh, because we predicted them ahead of time, right? Well, carbon prefers 4 bonds, right? 1, 2, 3, 4. So it cannot go to any of these. Hydrogen, it can never go to hydrogen. That would give it 4 electrons. This carbon has 2, so it wants 2 more. This carbon only has 2, so it wants 2 more. Interesting. This carbon has 3, so it wants 1 more. Oxygen prefers 2, right? Oxygen prefers 1, 2 covalent bonds. So that oxygen's happy, isn't it? This oxygen is not happy. Would you agree? So I would say one of those should go right there. You see that? That now gives oxygen 2 bonds, which it likes, and this carbon has 1, 2, 3, 4. So now both the carbon and oxygen are happy. And if you were familiar with carboxylic acids, it's the COO group, COOH, carbon double bond oxygen, OH. That's a carboxylic acid. Right? And if we put an amine on this side, NH2, we'd have an amino acid. Oh! Okay, anyway. Now, that takes care of 1. We have 2 more multiple bonds. So that's either 2 double bonds or a triple bond. Could we put a double bond here? No, because that would give that carbon 5 bonds. So it can't go there. It can't go there. So the only place left is here. That's the only place multiple bonds can go. Can't go here. Can't go there. Can't go there. Can't go there. Can't go there, because that would give that more than 5. So the only place it can go is here. And that gives us 2 extra lines. We need another one. Oh, it just falls into place. Do you see that? So now we've got 1, 2, 3 extra multiple bonds here. We have 1, 2, 3, 4 bonds to that carbon. 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 2 bonds to that oxygen. 2 bonds to that oxygen. Everything has their preferred number of bonds. Woo! Looks scary, but not that bad. All right. So now let's complete the octets. You ready? Hydrogens are done. This bromine has only 2, but it wants 8. So 2, 4, 6, 8. So you'll find halogens, their favorite thing in a Lewis structure environment is a single bond with 3 lone pairs. Halogens love that. Carbon likes 4 covalent bonds. See, this has, a triple and single. This has 4 singles. Carbon doesn't care as long as it has 4 bonds. So 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Carbon doesn't like lone pairs. 2, 4, 6, 8, 2, 4, 6, 8. right? All of the chalcogens, the oxygen, sulfur, they love 2 covalent bonds and 2 lone pairs. That's their preferred situation. So now everything has the octet rule satisfied. Everything has the preferred number of bonds. Let's count up the total number of electrons. Hopefully it equals 38. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38! Ho, ho, ho! Yes! Happy face. Check it off. 38 equals 38. Thank you for the 10 points on the test, doc, or coach, or prof, or whatever you want to say. If you can do that, you can do just about anything. Not too bad when you work your way through it. You got it, gang. Let's do some crazy stuff next.